Hello everyone. Today we're talking about two important discrete random variables. The goals are to be familiar with the binomial distributions, its requirements, probability mass function parameters, and how to compute probabilities with it. For the Poisson distribution, we need to be familiar with the model and its uses. Specifically know the requirements to use, when can we use it, when can we not use it, what its probability mass function looks like, its parameters, and how to compute probabilities with it. Know when we can use the Poisson distribution to approximate the binomial distribution. So we're going to cover all of that today. I want you to consider two examples. One might be in a batch of 50 widgets with a defectiveness rate of 0.02. What is the probability that 3 are defective from a batch of 50? Is that likely? Unlikely? How often do we expect 7 or more separate homicide events in England and Wales in a single day? Is that unusual? If it's unlikely, how unlikely? And how warranted is it to prepare for 7 homicide incidents? Getting these probabilities helps answer this important question: is it a fluke or not? That's behind the theory of significance. Is it significant or not? Okay, let's dig in. So the first distribution we're going to be talking about is the binomial distribution. To use a binomial distribution model, the following requirements must be met. There is a fixed number of trials. The trials must be binary, meaning either yes or no. The trials must be independent, which means one trial being successful does not alter the probability that the next trial will be successful. The probability of success is the same for each trial. If that's the case for a series of trials, like flipping a coin, then this is a binomial distribution. Okay, here's some examples or non-examples. So can we model with a binomial distribution? How many people are right-handed in a group of 200 randomly selected people? Yes, that is a question of how many successes. Whether a person is right-handed is the trial, and there's 200 randomly selected people. So that would be 200 trials, and this right-handedness is binary. In 460 NFL games determined by overtime, how many times did the team that won the toss win the game? Whether somebody wins or loses the toss is binary. There's 460 times this happens, so that's a fixed number of trials. This right here can be made to fit in the framework of a binomial distribution. We can leverage the theory behind binomial distributions to answer this question. In 2011, they got rid of the overtime rule. It favored the team that won the flip. We may talk more about that in class. How many defects does a Ford F-150 have right out of the factory? This does not fit into the binomial distribution framework because there is not a fixed number of trials. It's not like somebody has a clipboard of a fixed number of equally likely defects and they're just checking it off. That's not what's going on. There could be many hundreds of defects depending on how closely they're looking and what the parameters are, what the tolerances are. This does not have a fixed number of binary trials. Okay. The binomial distribution. Let's take a look. This is the mathematical description of the binomial distribution. This is the notation. We use a big B and we put in the parameters for the distribution. The first parameter is the fixed number of trials. Remember, that's part of the requirements. There has to be a fixed number of trials represented by n. P is the probability of a success for each trial, same for all trials. Q is the probability of failure. You'll notice P plus Q equals 1. X is the total number of successes. This then, actually, this interesting formula gives you the probability of X successes among N trials with probability P, and Q is a function of P. So all of this is determined by X, N, and P. Now, what do these look like? Look at this first plot. When N is 6, there's only 6 trials, and the probability of success is 20%. This gives the distribution the likelihood of 0 successes. So 0 successes happens at a likelihood of about, 25%? 1 success happens with a likelihood of I don't know, 39%, it seems to look like there. This one here would be a little bit less than maybe 23%. That's the probability of getting 2 trials among your 6 total trials, and so on. This one up here is when you have 10 total trials, and the probability of success is again that 0.02. Now you have 10 trials, the probability of no successes is only 10% likely that you will get no successes. And look at the probability of all of them being successful when the probability of a success is only 20%. The probability of getting 10 successes is minuscule. It's very small. It doesn't even show up on this plot. All right, and then this example here is when there are 20 trials. Okay. That's the mathematical description. Let's take a look at this example. A study in the Journal of Hand and Microsurgery states that left-handed people make up about 11% of the population. So left-handed, right-handed binary, probably a binomial distribution problem. What are the chances of getting a random sample of 100 people and finding that 20 are left-handed? N is clearly 100. Each person represents this binary trial. What hand are they? What hand dominant are they? N is 100. P, the probability of success, a left-handed person, is 0.11. Q is 0.89, which is 1 minus P. And X, the number of successes, is 20. The probability of success is normally a binomial distribution with 100 for N and 0.1 for P. This is a binomial distribution because there is 1, a fixed number of trials, 100. 2, handedness is effectively binary. 3, they're independent of each other. If I'm randomly selected and I'm right-handed, that is not going to affect whether the next person selected is left or right-handed, so the trials are independent. 4, the probability of success is roughly at 11%, because 11% of the whole population. Okay, now, depending on the population we're drawing from, which is everybody, remember the cumbersome calculation guideline says that if you are sampling less than 5% of the total population, these samples can be regarded as independent. So that is being used right. Otherwise, if I were to draw one from the population, we would have to recompute the percent left-handed. Without replacement affects the probability of getting somebody of that from that class, from that handedness. So the cumbersome calculation guideline comes to the rescue and says we can regard each of these draws as being with replacement, which does not change the probability of success. Now, let's get to the question, what are the chances of getting 20 left-handed people among your group 100, which is a little more than we would expect. We would expect 11, but there's 20, so that seems unlikely. Okay, but how unlikely? We're looking for the probability that our random variable x equals 20. That is the same thing as f, our distribution here, of 20. Okay, now I am not going to plug 20 into this big nasty formula because there would be 100 factorial on the top, which is an intractably large number. So instead, what I am going to use is I'm going to go to Excel, and I'm going to type in Poisson. I'm going to use the distribution Poisson.dist, and I'm going to enter it using Excel. I'll show you. Pull up just a normal Scratch worksheet, Excel sheet, and let's compute this probability. So I'm just going to say n equals 100, p equals 0.11, x equals 20. All right, and so now the probability p of big X equals little x. Let me make that one. So I made that a little x. That probability is going to equal Poisson.dis. X is going to be that 20. Okay. Hold on. Starting over. And so I'm not going to plug it into that big nasty formula. Instead, I am going to use Excel. I am going to use the binomial distribution in Excel. And I'll show you how that is to be done. So I'm going to get my keyboard. I'm going to go to Excel. Here's some stuff that Okay, let me show you how that is to be done. I'm going to get out my keyboard. I'm going to go to Excel. I've got here a blank notebook, and I'm just going to start typing in my data. So n is going to be 100. That's the number of trials. P is going to equal 0.11. And so the probability of my random variable equaling 20 in this case is going to be, let me go ahead and put that in. So that probability is going to equal, I'm just going to type by number of successes, 20, trials, n, probability of success, this one. Now, do I want cumulative? Cumulative is, remember cumulative frequency? How we would add up the number of occurrences in that class or fewer, or the classes underneath it. We want the probability of 20 successes. So I'm going to make this cumulative. I'm going to make it 0. That's a very important distinction to remember. We're going to use 0 because I want exactly 20. I don't want 20 and below. If I wanted 20 and below, I would put a 1 there. We just want a 0 there because we want 20 exactly. Enter. And there's my probability, 0.003, 0.3%. That's how likely it is to get 20 successes out of 100 trials when the probability of a success is 11%. So this is going to be binom 20, 100, 0.11, 0, and that equals 0.003. So 0.3%, very unlikely. If a study sampled 100 people and 20 were left-handed, the likelihood is 3 in 1,000. It isn't necessarily terribly unlikely, but it's very suspicious. I would suspect that the population from which they sampled these people had an unusually high number of left-handed people, meaning their sample was not representative of the whole population. Okay, so that's our binomial distribution. In section 4.3, example 4.11, is excellent. Pages may vary a little bit. On this slide, and we'll be looking at this slide, please summarize this example and include the solution. I don't want anything very lengthy, just please summarize it the best you can. You never know if it'll help you on an exam, on a celebration of knowledge, and anyway, as I said, the TA and I will be looking for it. Okay, that is binomial distribution, and of course, we will talk more about that in class and really solidify understanding. Let's talk about the Poisson distribution. To use a Poisson distribution model, the following must be satisfied. There is a fixed interval, not a fixed number of trials this time, a fixed interval. The events that you're counting how many events occur within that interval. Generally, an interval of time, such as customers coming into a store. The event would be the customers coming into the store. The interval would be maybe within an hour. How many customers came into the store during that hour or during that day? But it doesn't have to be with reference time. For example, we saw the number of defects on a Ford F-150. The Ford F-150 is the interval, and the number of defects could be the event that's occurring. So it must occur at random. And occurrences must be independent, which may not be the case with the Ford F-150 example, because with the assembly line process, some defects tend to be clustered and depend on each other. Maybe that's not the best one. However, it wouldn't stop you from trying the Poisson model. Here are some examples. Can we model these with the Poisson distribution? How many times a customer enters a store at a given hour? Yes, we can. There's a fixed interval, and there is an occurrence or counting. Generally speaking, they come in at random. This would be because, in general, customers, do people shop alone? Perhaps in some stores, people are more likely to shop alone in others. But if customers are usually shopping alone, then they're just going to come in and it's going to be independent of other customers. But this one here is in general close enough, basically. Okay, Mars Inc. claims 16% of M&Ms are green. How many green M&Ms are in one 1.69 ounce bag? All right, now what is the fixed interval? Is it one bag? You should not use a Poisson distribution to model this. The reason is why I would not use a Poisson distribution to test this claim of 16% of the M&Ms in the bag are green M&Ms is because there is a structural limit on the number of M&Ms that can be put into the bag. And so that's a little bit different from other times that you would use a Poisson distribution. Generally, there is no structural limit to occurrences. The occurrences are not independent. If there's a lot of green M&Ms that have already been put in the bag, another green M&M being put into the bag becomes less likely. These are not independent. So the more green M&Ms you put in, the less likely there'll be another green M&M added. Okay, and then how many defects does a particular Ford F-150 have right out of the factory? Again, this one here with a bit of an approximation. This one it'd be fairly reasonable to use a Poisson distribution to model the number of defects. Let's talk about the mathematical description of the Poisson. The Poisson distribution has one parameter, mu, the average or expected number of occurrences in an interval. X is the number of occurrences within the interval, of a particular interval, you might say. The probability mass function is a little bit easier than the binomial distribution. Here are three plots. When the average occurrence is 5 times per interval, 5 times per day, 5 times per year, then these give you the probability of there being a day or a year in which there's only 3. Let's say that's 2. This is 0. The probability of there being 2 occurrences when 5 are expected is 7%. There's a 7% chance of that. If all other requirements are approximately met, you can interpret this in that way. So the probability of there being 10 occurrences when 5 is expected for a Poisson situation, that probability would be, something like 0.2 maybe. Sorry, 0.02. When an average of 3 occurrences is expected, this is what the distribution will look like. And when 10 occurrences are expected, this is what the distribution looks like. Notice the mode is always near the average here. There's a skewness. This one is right skewed. Poisson distribution example. Between April 2014 and March 2016, 1,095 days, there were 1,545 homicides in England and Wales, an average of 1.41 per day. How often would we expect 5 homicides in one day? This fits the Poisson distribution because there's a fixed interval of one day. Occurrences are random. And 3, it's not unreasonable to consider these to be unrelated, right? One crazy usually just works alone. And those are fairly unrelated, so that meets the independence requirement. I'll just say again that when you model something, you just try and see if it works most of the time. And so these requirements can be met approximately, and you just see how well it does. Hopefully you have some way of verifying that it's a good fit, which we have here, and I'll show you how that's done. Let's use the Poisson distribution to answer this question. How often would we expect to see 5 homicides in one day? Let's start by finding the probability of there being 5 homicides in one day. My average is 1.41 homicides per day. The number of occurrences I'm interested in is 5. The probability of my big X, my random variable, equaling 5 is going to be equal to, now again, I'm not going to use that formula necessarily. I'm going to appeal to Excel. I'm going to use Poisson.dis, and I'm going to fill in my information. Let's go and do that. So before we used Binomial, and now we're going to use Poisson. So what? I need my mu, and my mu equals 1.41. Let's find the probability. So P of big X equaling my little x, which is 5, is going to equal sign. So Excel knows I'm typing in a formula. POI, Poisson.dis. X is going to be 5. Mean is 1.41. Cumulative is 0. I just want the probability of exactly 5. So do not accumulate them. Keep it at 5. Enter. 0.01134. Okay, back to notability. So that was, what did we type in? We typed in 5 for the X, 1.41 for the mean, and 0 for that cumulative argument. And we got 0.01134. Okay, now that gives me the probability of there being 5 homicides in one day, but I want to know how often I can expect 5 homicides in one day. Does this value give us that? Well, this value is the rate at which it occurs. Remember the relative frequency definition of probability. This probability we found is approximately the number of times 5 homicides occur over total. So remember the relative frequency definition of probability. This thing is approximately the number of times 5 homicides in 1,095 days, we would expect to see about 12.4 days. Okay, so this probability is the number of occurrences over the total days. If we multiply by the total number of days, we recover the number of occurrences. And so that's what we would expect to see. According to the actual data, out of 1,095 days, there were, in fact, 13 days in which there were 5 homicides. So I'd say that worked out pretty well. Let's take a look at the Poisson distribution now. Okay, so when does the Poisson distribution get used? Well, as it turns out, it can be used to model a lot of different things. Number of wrongful convictions per year, goals scored by a soccer team, winning lottery tickets, Prussian officers kicked to death by their horses each year, and much, much more. And so this thing here in particular is very important to have a pretty good estimate of how likely it might be for so many lottery tickets to win. Although I guess if more than one ticket wins, they'd share the pot. But some things, like if you could use the Poisson distribution to predict or to give a good probability for the number of hurricanes, maybe, that would be useful information. You could see what the likelihood of so many hurricanes in a year might be, get an average amount of damage done, and be able to, if you were an insurance company, you would set your premiums in order to make that, in order to handle most years. Well, these sorts of models are something insurance companies look into. Random variables have parameters. The average value of the binomial distribution is the number of trials times the probability of a trial. So before there was 100 people, 11% of the population is left-handed. We would expect 0.11 times 100, or 11 people, to be left-handed. The variance is n times p times q, and the standard deviation is the square root of that number. For the Poisson distribution, the mean is equal to the mean you're trying to model. What's very interesting is that the variance is equal to the mean. So whatever the mean, if the mean is bigger, the variance is bigger. The standard deviation is the square root of the mean in that case. So that's really only true for the Poisson distribution. That is not true in general. Okay, in some cases, you can use the Poisson distribution to approximate the binomial distribution. If n, the number of trials, is greater than 100, and n times p is less than 10, remember this right here is your mean for the binomial distribution, then you can use Poisson to do that, and we're going to see an example. And we are going to see an example of that. So that's the mean you use for the Poisson distribution. I would like to see that example. Let's skip over this hurricane example and look at the main pick 4 game. You pay 50 cents and select 4 digits from 0 to 9. What is the probability that you will win if you play every day for a year? You win by picking the correct 4-digit number. What are our trials? The trials are every day for a year. For the binomial case, we have n equals 365. What's the probability of me winning on any given day? I need to pick 4 digits from 10 choices. I've got 10 choices, 0 through 9. And so there is 10 choices for the first number, 10 choices for the second number, 10 choices for the third, and 10 choices for the fourth. And so that gives me 10,000 different combinations, each equally likely to be drawn. At least that's the idea. So I've got 1 in 10,000 chance of being successful. And what is the probability that you will win if you play? What does that mean? So x equals, well, I just need to be successful once. That's the probability of winning once. But I could also win twice, 3 times, all the way to 365. In order to get the probability of winning, I can use my complement rule. Remember, at least once? This is winning at least once. That is the probability. That's 1 minus the probability of never winning. And so that probability is going to be, so the probability of never winning is going to be x when x equals 0. That's the probability of my binomial random variable equaling 0. What that is going to equal is binom dot dis of 0 x n trials, if I'm not mistaken, and times 1 over 10,000. And then 0, because I want it when it's just 0. I'm going to figure out that number. But before I do, let's look at using the Poisson distribution to approximate my binomial distribution. With Poisson, I have those requirements that I need to make sure are satisfied. So n equals 365, and that is bigger than 100. Okay, that requirement's met. What about n times p? Well, that's going to equal 365 times p, so that's 10,000, which equals 0.0365. That is my mu, and is less than 10. So I can use the Poisson distribution to approximate, and let's see how close we get. So for this one, I'm going to do the same approach. I'm going to find the probability of never winning. And so that's the probability of x equals 0. That's Poisson dot dist. In the parentheses, I put 0 for my x, and then for my mean, I'm going to put 0.365, and then cumulative is 0. Let's go to Excel and see. Okay, let's do binom and Poisson. For binom, p of x equals 0 is binom dot dist, number of successes, 0, number of trials, 365. Probability is 1 divided by 0, 1, 2, 3, 4 zeros. Cumulative is 0. Enter. 96.4%. That's the probability of not winning at all, never winning. So now I'm going to do the same thing, but I'm going to use the Poisson distribution to approximate it. Equals Poisson dot, there it is, x is 0, mean is going to be 0.0365, comma 0, enter. Look at that. It's the same number. It's the same. It gives me the same probability. Very close. Not exactly. If I click on that number, I thought it might show more decimal places. So they're not exactly the same, but they're close enough. Let's go back. The probability of winning is 1 minus the probability of never winning. That's 0.0, let's round it. This was 0.96416. So the probability of winning is, as Excel told me, 0.058. No matter which way you slice it. If you use binomial, you use Poisson, you'll get the same result. Let's do one more Poisson example. In the 59 years from 1960 to 1918 to 2018, there were 366 hurricanes in the Atlantic Basin. How well does a Poisson model predict the likelihood of there being 8 hurricanes in a single year? Okay, so what's the likelihood of there being 8 hurricanes in a single year? Can we use the Poisson model? So the fixed interval is years, 1 year, 1 year. Does it occur at random? Yes, it's sufficiently complex to say it occurs at random. Are they independent? Maybe this independence is not as strong as we would like, but they seem to happen fairly sporadically. You could have some pretty close together and some not close enough. Let's see how it models. If it doesn't model very well, maybe we can blame independence, lack thereof. Okay. All right, so I want to do a Poisson model. What do I need to make a Poisson model? I need the mu, the expected value. That's going to be 360 hurricanes over the total years. There were 59. I type in 366 divided by 59, and I get 6.20 hurricanes per year. That's the average. So my mu is 6.20. My x is 8, because I'm concerned about 8 hurricanes. And that's all I need for Poisson. I want big X to equal 8. To solve that, I'm going to use Poisson. X is 8. Mean is 6.2. Cumulative is 0 because I'm concerned with exactly 8. I don't want the probability of it being less than 8. I want 0 for that entry. P of X equals 8 equals Poisson.dist. X is 8. Mean is 6.2. Cumulative is 0. Probability is 0.1099. How well does the model predict the likelihood of there being 8 in a year? That is the probability of there being 8 in a year. And so that is an approximation of the total number of years with 8 hurricanes divided by total number of years. That's the relative frequency approach to probability. So I can use this model, multiply the total number of years by this number. I should recover the number of years that there were 8 hurricanes. All right, and what do I get? I get 6.481, so about 6.5 years, because this is years. Okay, let's take a look at this next slide. Turns out there were 6 years in which there were 8 hurricanes. If I rounded it to the nearest year, I would get 6, which agrees with this model. Very interesting how we were able to, well, accurately predict the number of years in which 8 hurricanes occurred. Now, this plot shows me the bar chart. It gives the probability of the Poisson distributions in bluish purple color against the actual data, which is in that gold color, that orangish color. What do you make of this plot? See, so the gold is telling me what the actual data is, and the purple is telling me what Poisson would predict would be the frequency. So this is frequency here. I should have labeled this relative frequency. And this right here is number of hurricanes. Let's see. This one is 9, 8, 7. This range is quite good. The model does a very good job with each one. The other ones, not very good. Maybe we can blame independence. The occurrence of the hurricanes is not as independent as we would hope. This one here is not good. This one is okay. These are off. But on the whole, it's not all that bad. It does a pretty good shape. Modeling is rather difficult. And we're also dealing with small n effect here. Okay, so just like when we were rolling our dice and we really only rolled it, we only rolled it about 400 times, and the histogram looked really erratic. We shouldn't be too surprised at some behavior like that when here we only have 59 years. So that's a very small n. That's Poisson. Insurance companies are using stochastic models like Poisson to identify the likelihood of so many hurricanes. What's the likelihood of there being 10 hurricanes in a year? It's about 0.05. Maybe it's warranted to charge premiums according to that estimate. Of course, that's oversimplified. Recap. We talked about the binomial distribution. We talked about the requirements in order to use the binomial model. We talked about the probability mass function, which was a little bit hairy, but we just use Excel. And we also talked about the parameters. Then we talked about the Poisson distribution. The requirements must be satisfied to model a situation. We also talked about the PDF, which was better than binomial, but not by much. We talked about the parameters. We talked about how the Poisson distribution can be used to approximate the binomial distribution. We showed how to compute these in Excel/Sheets. Sheets uses all the same formulas. Okay, we also looked at some examples. That's it for today. Thanks for watching. I'll see you in class.